Okay, I guess we can get started. Hello, everybody, and welcome to today's event on the networking channel. We will be having an event today called LEO Satellite Mega Constellations, the New Space Potential. It will be organized as a panel, and we're very lucky to have two incredible experts on satellite systems leading the panel. We have Nishanth Sastry, who's Director of Research in the Department of Computer Science, University of Surrey. He is joint head of the Distributed Network and Distributed Systems Group. He is a Surrey AI Fellow and a visiting researcher at the Alan Turing Institute. We also have Debopam Bhattacherjee, who is senior researcher at Microsoft Research Bangalore. His research has made extensive breakthroughs and contributions in the field of satellite networks, and he has won numerous awards for his work, including a number of Best Papers awards and the RTF's Applied Networking Research Prize. They will be joined by a panel of very esteemed and highly accomplished experts in this space, covering a broad swath of industry and academic research. Before we start, we also want to mention that the networking channel is a series of talks happening every 2 weeks. This is going to be our last event of 2023. We will continue in January 2024, and we have some very exciting events that are going to be announced soon. We hope you will join us for those. And with that, we can start the panel for today. One of our goals is to keep things informal, to make it easy for all of you to join in and guide the conversation towards your interests. We would like to invite you to interact with the panelists. All our events are interactive. You can ask questions on Zoom using the Q&A feature at the bottom of your screen. If you would like, you can also enable closed captions if that is helpful for you to see what is being transcribed as text on your screen. We now have translations if you would like to see the words translated into your favorite language. And if you don't get your questions answered during the event, you can also join our Slack workspace and keep in touch with the panelists there as well. So I will now turn things over to Debopam, who will be beginning the panel. Thank you.
Thanks, Matt. Let me quickly share my screen. Okay, just a moment. Yep. So hello, everyone, and welcome again to this very exciting session on satellite constellation opportunities and challenges. Thanks for the introduction, Jim. And I really thank Jim, Matt, Ranjita, and all the other steering committee members for giving Nishanth, Mohamed, and me this incredible opportunity to organize this event. We have some great speakers lined up today. So without waiting anymore, let's go through today's agenda. We'll have this quick intro from me first, followed by 5-minute talks from our speakers today. Finally, we'll open up the floor and discuss broad questions of interest in this area. I request the audience to use Zoom's Q&A or chat feature to send your questions online. I also request the panelists to continue the discussions on the networking channel Slack channel offline. Okay, so changing gears now, let's see what is so exciting about the LEO satellite stuff. The low Earth orbit or LEO satellite revolution is seeing significant traction along 3 key verticals. Many mega constellations consisting of tens of thousands of satellites are currently being rolled out to offer global low latency internet connectivity. The second major transformation is happening in the Earth observation industry with satellite imagery and Earth sensing constellations sending huge volume of data to the cloud for processing. And third, the space industry aims to deploy compute on orbit with many important use cases like data compression and inferencing in space. Over the last few years, leveraging advances in reusable boosters, compact satellite design, and space laser tech, many industry players have entered a space race toward offering innovative services to large markets. Government agencies have started opening up and are heavily collaborating with private players. And this has reflected in the broad community interest in this area, even at top tech conferences. We have been active in bringing this space/systems research community close together. While Ankit Singla and me started the LeoCon series of events back in 2021, Nishanth, Mohamed, and me are organizing regular LeoCon web events. Mohamed also recently co-organized LeoNet workshop at Mobicom. Across multiple panels, we have observed a community urge to run LEO experiments at scale. Hence, toward enabling LEO broadband research more broadly across the community, we are building and deploying a global LEO broadband testbed named LeoScope, similar to Planet Lab or Ripe Atlas for the terrestrial internet. The testbed will consist of LEO user terminals from across the globe, which could be leveraged for running end-to-end experiments over different LEO broadband networks. The one on this picture is a real deployment. The testbed will also consist of a cloud-hosted orchestrator and multiple measurement servers, and needs decent engineering effort to accommodate the new setup and some useful features. As listed here, this real testbed will enable a plethora of interesting experiments that are needed to understand and innovate over these networks. The first version of the testbed code has been recently released, and the deployment is in full swing. This is a snapshot of what is coming. It's a go-to portal for all your LEO experiments. Stay tuned for more announcements from us soon. Also, for early access or to contribute hardware, please get in touch with Nishanth, Mohamed, or me. Finally, I'd like to acknowledge an incredible team that is making this platform possible. Special thanks to Shubham for bootstrapping this effort. And with that, I'll hand it over to Nishanth for coordinating the speaker presentations. Thanks.
Thanks, Debopam. So we've got a bunch of very exciting speakers who are kind of leading or pioneering this new and emerging field. We start off with Lili Chiu first. Lili, if you'd like to start sharing your screen. Lili is a professor at University of Texas, Austin. She's also an assistant managing director of Microsoft Research Asia. She's mainly responsible for overseeing the research there, as well as collaborations with industries, universities, and so forth. She's an IEEE fellow, an ACM fellow, and an NAI fellow. She also serves as the ACM SIG Mobile Chair. She was named as an ACM Distinguished Scientist and was a recipient of the NSF Career Award, among many other honors. Lili, the floor is yours.
So let me reshare my screen. You all see my screen?
Not yet for me. Yes. But not in screen show mode. Yes.
Thank you so much for the wonderful opportunity for sharing our recent work on applying Metasurface on LEO or in general innovating intelligent environment, a new perspective on wireless communication. The advancement of wireless communication followed a theoretical guideline. Consider we have a wireless system consisting of the transmitter and receiver, each with multiple antennas. Shannon capacity indicates increasing the number of antennas allows us to achieve higher capacity. And this has inspired lots of work on improving the transmitter and receiver, such as developing massive MIMO. These techniques are very effective in improving wireless capacity. But on the other hand, it comes with significant cost of hardware, computation, and power. Is there an alternative way to achieve high capacity and reliability? Let's revisit this wireless system. As we know that the wireless system performance is not only dictated by the transmitter and receiver, but also by the channel in between. In the past, we have assumed the wireless channel is fixed and given by the environment and we cannot change. But our proposal is that we want to innovate intelligent environment for wireless communication by placing low-cost structure in the environment to create a more favorable wireless channel to support wireless communication. To achieve low cost, so here's an example. Consider we have a VR user, and as he turns his head, then the VR headset may not face the wireless antenna, so he cannot get wireless signal. How to address this? One possibility is we can place a reflector in the environment so that the reflected signal reach the headset. But what if the user had moved further? We may not be able to find a reflector to be placed in the environment so that the reflected signal go directly to the headset. This is because the conventional reflectors or the refractors, they follow strict law of reflection and refraction, and these are quite restrictive. So is there an alternative solution? A Metasurface is an exciting breakthrough that originated from optics and more recently applied to wireless communication. It can more freely modify wavefront by changing the phase, amplitude, and polarization. So the working principle of Metasurface is follow. A Metasurface is an artificial 2D structure that consists of many sub-wavelength cells. Each cell consists of, you can view it as a mini antenna. So the entire Metasurface can be viewed as an antenna array, but different from traditional antenna array, which require excitation source to generate signal. Metasurface can be excited by incoming electromagnetic wave. By carefully designing the unit cell, we can modify each unit cell's the outgoing signal from each unit cell's phase and amplitude. And the cumulative effect of this local response lead to very exciting global phenomena such as beam steering, focusing, polarization conversion, and so on. And we apply Metasurface to LEO orbit satellite communication. This is inspired by the fact that even today, still 1/3 of world population do not have internet communication. And LEO satellite communication has the potential to offer high speed, low latency, and the satellites are relatively easy to set up. And the launching cost of satellite has rapidly decreased, and several companies has already launched or are planning to launch thousands of LEO satellites. We choose to use a passive Metasurface to achieve low cost, and there's no power required for passive Metasurface. It's a 2D structure that we can easily place on the windows to reshape the outgoing wavefront. And it is a very low cost. But one limitation of passive Metasurface is that once manufactured, it is fixed. But since the LEO satellite communication, when the satellite is constantly moving, we want to support the signal coming from arbitrary directions for both incoming and outgoing signals. Therefore, we combine the programmability of small phase array antenna with the powerful wavefront shaping of passive Metasurface to achieve the best of both worlds, the low-cost dynamic adaptation. Our Metasurface design consists of two parts. One is the microscopic design, and the other is the macroscopic design. In the microscopic design, our goal is to seek a unit cell template such that it can achieve high transmittance, large phase shift range, and support wide incident angles. And also, LEO satellite communication use different frequency for downlink and uplink. We want to design a single Metasurface that can support dual band communication. And we identify this following structure. It consists of 4 layers, and each layer has this design pattern with the air gap in between. And this allows us, and meanwhile, in order to support both uplink and downlink, we have 2 types of structure. And this part is support the downlink communication, and this part is used to support uplink communication. And we are able to achieve high transmittance, as shown in this figure, and also large phase shift range, close to 2 pi phase shift for both downlink and uplink here. Next, we need to design the entire Metasurface. Basically, for each template at every position, now we need to determine the exact unit cell to be used at each position. To do that, we formulate this as an optimization problem. Basically, a transmission signal is determined by the code word, and then the signal will reach the wireless channel edge, and then finally arrive at a Metasurface. We want the outgoing signal or incoming signal to be maximized in certain direction towards the satellite. And this can be cast as an optimization. And then we use the gradient descent to solve the Metasurface phase offset at each position.
Thanks, Lili. That's fascinating. Maybe if you could wait until the question and answer for some of the details, because this is really fascinating. But we have also the time limitation as well. That's okay.
Shall I finish or shall I
Yeah, if
stop
this is the
here?
last slide, then yeah, please finish this slide and then we can carry on.
Okay, yeah, finally we arrive at this Metasurface. So these are the Metasurface, and this is the transmitter and receiving antenna. It's a very small phase array, only 4 antennas. And then we place our transmitter at a high-rise building, 43rd floor, and then put the ground station on the street. And this is a Metasurface we place on top of the transmitter and receiver ground station. And we are able to observe up to 45 times the signal boost. And the total cost of our Metasurface is only $76. And in fact, with this recent enhancement, we are able to even reduce this cost by another order of magnitude. And in comparison, the equivalent function phase array will have an order of magnitude higher cost. And beyond applying this Metasurface to LEO satellite communication, we also applied it to wireless sensing and millimeter wave coverage problem. And our vision for the future is, given the environment and application requirement, our system can output the transmitter and receiver design as well as the Metasurface, and these designs are jointly optimized. And this allows us to achieve network coverage, high capacity, low latency. Meanwhile, it can also be used to realize powerful sensing to empower AI with sixth sense. Thank you, everyone.
Thanks a lot, Lili. We should move on quickly to the next speaker, who is Aravindh Raman. Aravindh is an internet measurement researcher who has broad interests in global connectivity through mobile and satellite networks, as well as the decentralized web. He's an ISOC fellow, and he currently works at Sky UK and was previously at Telefonica, Spain. Aravindh, over to you.
Sorry, I was muted. Sure thing.
5 minutes, that would make it easier for the rest of the panel as well.
Yep, starting the timer now. So thanks, Nishanth, for the introduction. I hope everyone can hear me. So in this talk today, I'll be trying to cover the challenges and opportunities in measuring the current state of LEO broadband and touch upon some of the factors affecting this satellite network performance. So why it's important? So as everyone here probably know, the increase in the number of satellites being launched, especially more than 90% of the satellites launched in LEO space happened in like past 3-4 years. So it becomes like kind of bursty traffic, as we call. So the bottom 2 figures here shows like the satellites up in the sky for Starlink and OneWeb in different constellations. So how we do it then, because given the global coverage and multiple satellite network operators, it becomes harder to measure all these networks. So how we do it is use multiple techniques to study the current state of the satellite networks and try to characterize them. So the first way is we started with probing, starting Facebook ads and Reddit post and trying to hire volunteers who would be running our test suite. And these volunteers would be using Starlink back then. And then we slowly moved on to look at public data sets like MLab, RIPE, and data sets published from RIPE, CADA, etc., to see what are all the factors that's affecting the LEO broadband. And this was followed by recruiting users from crowdsourcing platform called Prolific and trying to study again, running bit more high-level experiments, because the public data sets don't give high-level video conferencing or video streaming. So we had to hire users from this crowdsourcing platform. And then finally using LeoScope testbed to run bit more fine-grained and temporal experiments. Thanks to the testbed, we were able to run across different countries. So I won't be going through all the factors here, but I'll try to give a brief overview and maybe highlight something important. So in this figure, x-axis gives like various operators, various satellite network operators, and y-axis shows their latency. Even within LEO, for example, Starlink and OneWeb are like have like 50% or more than 50% of latency variation when you take the median. So this says something. Obviously, the main factor here is the orbit they are placed. So, I mean, it depends on whether it's LEO, MEO, or GEO, but even within LEO, you have such a variation. So one way to tackle this would be like have a cooperation amongst these operators, but I don't know when that's going to happen. Like we have terrestrial network operators having all this policies for cooperations, but yeah, it's very much needed in the satellite space as well. So to go on to the other factors, starting from the state of atmosphere, so it can be weather that could affect the connection, location of the user. So these are like practical limitation. We can't do anything there. And the choice of the provider or the orbit. So we can have like multi-party agreement to reduce the number of launches. And we also noticed that the terrestrial connectivity matters. So once the packets reaches the ground station and how they are communicated to the internet, how they are traversed to the internet matters as well. And moving on from the infrastructure side, we also have like application side of things, like selecting the right TCP variant or selecting the right CDN within the application, as well as the protocol selection, whether it's HTTP 1 or 2, that matters as well. So if you think of it, like the top ones are very hard to change, whereas while the bottom ones are easier to change. As I told, like I'll try to cover a couple of factors here. So one is the weather. So in this figure, what you see, the weather of London, we were able to measure it in 3 days, given the weather of London varies like quite rapidly within 3 days. Here you see a difference of like around page transit time, which excludes the DOM load, etc. So it's time traversed by the packet in the network. It's around 500 milliseconds when there is a clear sky, whereas it goes closer to 1000 milliseconds when there is a rain. So we noticed that clouds don't play a major role, whereas rain play a major role when it comes to connectivity, especially with Starlink. Unfortunately, we can't. We weren't able to do the measurements with snow, but hopefully in the future we will do it. Also, there are other factors like satellite launches, which can be affected by geomagnetic storms, etc. And the terrestrial connectivity matters. So for example, where the user is located and where the packet is going to break out to the internet matters as well. So in this case, the user is in Alaska, whereas the packet breaks out to in a POP somewhere in the East Coast. So which introduces a delay of like more than 40 to 50 milliseconds. So how the POP connection or where the packet exits to the internet after the ground station matters as well. And to sum up, we have like variety of challenges from practical to applicated applications. Some of them can be easily tackled, whereas some of them can't be. And thanks to all the collaborators listed here. And I would like to welcome you to reading further more details in our CoNext and IMC works, which I have posted there. Thank you. Thank you.
Thanks a lot, Aravindh. Thanks for keeping on time as well. We move on next to Cristel and François. Cristel Pelsser is a professor at UCLouvain. Her research interests are in internet measurements, routing, and embedded systems. So we stay on the theme of internet measurements of Starlink. And then we have François Michel, who recently also obtained his PhD at UCLouvain, and his interests are in transport protocols, especially quick and network locks recoveries.
So can you hear us correctly?
Yes.
Cool. So we also performed some experiments with our Starlink access. So here we only did it with one vantage point. And we looked at more specifically at packet losses, delay, and the paths that satellites can take. So why we did that is that because I did my PhD in quick for loss recovery, and so we wanted to explore the loss patterns that could occur on the Starlink network. So we performed two kinds of experiments. First, some bulk experiments using HTTP 3. So it's using quick so that we ensure that there is no performance enhancement proxy on the link. So it's a heavy experiment that is focused on throughput. And then there is a light load experiment, which we call the message experiment. We send small messages at some interval at 3 Mbps. So it's significantly lower than the bitrate that you can ask for Starlink. So we want to, in the message experiment, we don't want to cause buffer bloat, basically. So we perform our experiments in our access in Belgium. So these are the photos of our access. And so the first thing that we looked at is the evolution of the measured round trip time during these quick transfers. And what we could see is that basically buffer bloat was present in our access in both ways. When you look at the bulk traffic use case, when we download a lot of data and we upload a lot of data, the round trip is significantly affected. For our light load experiment, it's the variance is significantly lower. Probably that because we had no congestion and so we had no buffer bloat. So we could observe some buffer bloat on the link in these experiments. Then we looked at packet losses occurring on the link. And also, so we first computed the loss rates in these two experiments. First, we saw that we have a significantly high loss rate for the heavy experiment, the bulk ones, and a lower loss rate for the light flow. Meaning that probably most of these losses are due to congestion, and these ones probably due to satellites changing focus. And so to observe that a bit further, we looked at the loss bursts occurring during the downloads. So we looked at the amount of packets that were lost consecutively. And so what we could see is that for the bulk experiments, even if the loss rate is really larger, the loss bursts on average are smaller. So congestion-induced losses were affecting less packets in a row. While for the message use case, the loss rate is significantly lower, but the losses that occur span a lot more packets consecutively. So probably that these losses are also present there, but the proportion of losses is significantly lower here. So we have less losses, but affecting more packets with our message use case. So probably that the medium losses are behaving like that. So now I hand the floor to Cristel.
So what we try to understand as well is how the routing happens in Starlink. And we wanted to know whether traditional techniques are applicable to Starlink, traditional measurement techniques. And so what we did is we took some RIPE Atlas probes. So here is one that is connected to our access in Louvain, La Neuve. And then we probed towards another probe that is in the US and towards the Google DNS server. The objective was to test the two types of connectivity and to try to understand the paths that are used and to reverse engineer a bit how the network is structured. So we wanted to understand what are the IPs we can see for the user segment, what can we see for the space segment, the ground segment, and then the terrestrial infrastructure as well. So we did some trace routes. So here you see on the left trace routes from Starlink to Starlink. So from Louvain in Belgium to the US and from Starlink to the internet. And so we have these sets of IPs. We try to understand, interpret the results. So what do we see? First, we try to see where the terrestrial segment starts again. So for example, here it starts again after hop 2 and 3. So we go to space and we see more or less nothing in the space, and then we go back. We have some carrier grade NAT, a private IP address, and then we have a set of IPs that belong to Starlink network. Then we looked a bit at the RTTs to try to understand what was happening. So what you can see here is, especially from Starlink to Starlink, you have very high RTTs, and it's because you have some MPLS in there. So basically what we can conclude from these measurements is that you are quickly back to Earth. And then for the Starlink to Starlink, you go from the space to Earth, back to space and back to Earth. So there is very little use of the space segment. So here are our conclusions, and we would hand the floor to the next presenter.
Thank you very much, François and Cristel. We next move on to Brandon Lucia. Brandon is a professor of ECE at CMU, Carnegie Mellon University, and he's also the CEO of the Efficient Computer Company. His research focuses on hardware and software systems, from new chips to architectures, to software and programming languages, especially for physically constrained environments. He's director of the NSF CPS Center for Software-Defined Nanosatellite Constellations, and he and collaborators are working to make collections of low-cost nanosatellites into highly capable sensor-equipped distributed computing platforms for future space-based cyber-physical applications. Over to you, Brandon.
All right. I assume everyone can see my slides and hear me talking. Object if that's not true. I am very happy to be on this panel today. This is a subject that I love talking about, and it's very interesting to learn from the other panelists and hear what you've been talking about. I think it's going to be a great discussion. What I'm going to talk about today is focused on the computational aspects of launching large numbers of low-cost nanosatellites to LEO. And the purpose of doing this is we want to support space-based cyber-physical applications. So that means a lot of imaging applications, RF processing applications. You can see some examples here where we might want to monitor infrastructure or do things like search and rescue or security type applications. These are cyber-physical applications because we're closing the loop on sort of both sides, where there's actuation involved in supporting these applications on the side of the satellite, and there's also a sort of physical response component if you look at the end use of the application on Earth in something like an infrastructure monitoring crisis response situation. So there's a lot of cyber-physical aspects to the applications that we can support, and it's a really exciting kind of new domain of applications. There's loads of research challenges in this area. I am not going to be talking about networking as much as the other panelists, and I shouldn't be. I'm here to learn about networking. I think this is great. Maybe I'll improve this slide after this panel. But I like to think about the challenges that exist if you try and, naively blast into this area and start doing computing research, which is basically what I did. One of the things you run into really quickly is if you launch a bunch of satellites and they all have big cameras attached to them and they can collect high resolution imagery, you can generate a lot more data than you can downlink. So here's a sort of notional picture with a little bit of some high level numbers attached, and I'd be happy to dive into the numbers more with other panelists and know more about this. You get about 37.5 gigabytes of data down per pass, and this is under fairly optimistic assumptions. And assuming well-positioned polar ground equipment and polar orbits. So if you launch a bunch of satellites and each one has a big camera, each one of those satellites continuously imaging and collecting 8K raw data. By the way, we don't want to do things like lossy compression because that introduces artifacts into the data and makes the data not usable for a lot of science applications. So we'll assume that we have raw data. Each one of those frames is 100 to 200 megabytes. Depending on your orbit characteristics, you might be getting new frames as frequently as every second or two, so 1.7 seconds. And now we can generate 634 gigabytes of data per orbit. So if you use that downlink that I just showed you, you're losing 83% of your data per orbit, which really sucks if you care about covering the entire ground track of your orbiting satellite. And if you look at hyperspectral data, you add more layers to the data that you're collecting in a wider spectral band through which you want to do observation. You're onto terabytes of data per orbit, and it's basically a nightmare if you care about getting all those bytes down. So what are we to do? Well, one of the things that we've been looking at is trying to just not use the network. We don't want to send the data down, and instead what we're doing is sending the processing up. The world is changing substantially. We've gone from these monstrous $650 million satellites where there's one or two of them launched every couple of years, and it takes nation state resources, to a world where CubeSats and pocket cubes can easily be thrown up into orbit, and they can have things inside of them like radios and lightweight actuators, and they can contain advanced processing for AI, ML type applications, and you can do that with things like the efficient low swap space-based computer architecture that we're developing at the Efficient Computer Company. And that's a new architecture that is dramatically more efficient than anything you can get on the market today. It could sit in there right alongside something like NVIDIA or something like other processors. The point here, though, is that we want to push high efficiency computing into the satellite so that we don't need to send the data to Earth. This is in scope of the Center that Nishanth mentioned in my introduction. This is the NSF CPS Frontier Center in Software-Defined Nanosatellite Constellations, and we're looking at this in a very holistic sense, from actuation to ML to control theory, motion planning, communications, and onboard computing. We encompass all of those aspects, and we look at how they serve cyber-physical systems applications that are built on these kinds of constellations. We're focused on autonomy. We're enthusiastic about the idea that these need to be software defined in the way that the cloud thrives, because it's essentially software defined infrastructure, and you can do anything with the resources that are out there. There are many components to the work that we're doing, and in the interest of time, I'm going to just skip over most of this. I'll give you the high-level broad brushstrokes, and then I think I'll stop just after this. We're pushing computing into satellites. There's an interesting link between computation, actuation, and the distribution of work over a constellation. And this is one of the key things that we're focusing on, is understanding what's the relationship between those and how do we exploit that. On-orbit learning at constellation scale is something that really hasn't been taken on in earnest up to this point, except with a few piecemeal efforts, and it's a very exciting opportunity in this space. Networking, you all know more than I do about that, so networking is a huge component. We need to figure out how to get the maximum value out of every bit that we send down, and we want to make space easy. So something that I'm really enthusiastic about too, in my kind of personal views on this and in the scope of the center, is I want space infrastructure to be easy. This shouldn't be hard. You should be able to deploy to a satellite. We're launching the satellites that I hope you'll be able to deploy to in the next 5 years. We're going to have a research constellation deployed as part of this center, where you'll be able to ship us a workload and we'll be able to ship it to the constellation. This is the goal that we have for the 5-year story arc of the center. We're already putting the pieces into place. We have made a series of satellites. We've had teams of students. Right now we have a team of 35 students building another satellite that's going to join our constellation of existing satellites. The video you can see playing in the lower right corner is actual launch video from one of our launches of CubeSat, and NanoRacks had cameras on board, so they were able to capture the launch vehicle as it left the deployer, which is very exciting. And all of this is a convergence of a lot of effort from students at CMU, faculty at CMU, the NSF support, and the support of industry partners, including Efficient Computer Company, where we're working closely together to develop the next generation of onboard compute hardware with novel computer architectures for space-based computer systems. So what we're doing is really exciting. We'd love to engage with you on this, and we're hoping to build that infrastructure that's going to make this easier for everyone. And that is it.
Thanks a lot, Brandon. And we move on to our final speaker, Ranveer Chandra. Ranveer is the Managing Director for Research for Industry and the CTO of Agri-Food at Microsoft. He also leads the networking research group at Microsoft Research in Redmond. And previously, he was a chief scientist of Microsoft Azure Global. His research has shipped in multiple Microsoft products. His research also led to a completely new product called Azure FarmBeats. So we're going to hear about some low latency real-time insights from his recent work there.
Thank you, Nishanth. And today, so I also manage the networking group at Microsoft. And today I'll talk about some of the work that the team has been doing on a big bet for the group on space and 6G. Today I'll focus on space, and in particular on Earth observation satellites. This is a cross-group effort where many of us across different groups at Microsoft Research, including Debopam, Lili, we heard from, and various people from my team, including Tushar, Kevin, Suraj, Shadi, Bodhi, all work together. We also work closely with Brandon on some of the work he's doing, and Deepak at University of Illinois, who's been a very close collaborator. We've had interns from different universities, and we also have people who work with the FCC and broadly across different teams as we focus on this overall effort. In the Earth observation space,
Ranveer, sorry to interrupt. Your slides are not moving. I don't see your slide.
But you don't see the full slides. Wait, I'll just quickly stop sharing and share again. Yeah. Do you see my the full screen now?
Yes. Yeah.
We see
no, but we see with presenter notes and everything.
Oh, okay. Just give me 1 second. Share screen. Hopefully this will be better.
Yes, perfect. Thanks.
Okay, cool. Thanks. Yeah, so just going back, yeah, we work with various people across different teams at Microsoft on this effort. These are just some of the collaborators. So today I'll talk about Earth observation. The other big focus in the team is on communication satellites. On communication, our key focus right now is on 5G NTN, that is non-terrestrial networks. But today I'll cover about Earth observation. So, Earth observation satellites, as you heard previously from Brandon and others as well, these are the satellites where you take images from space for monitoring events like, floods, crop stress, climate change, and so on, for tracking ships, how they're moving, tracking supply chain, and to disaster monitoring, be it, floods in Pakistan, wildfires in California. There are many such applications of Earth observation. In this talk, what I'll mainly talk about is these Earth observation satellites. These typical Earth observation satellites operate in low Earth orbit. These orbits are around 500 to 1,000 kilometers above the Earth's surface, and they have a period of about 90 minutes. As you can see, these satellites continuously go around the Earth and scan the surface, just like you have drones in the sky. So modern Earth observation satellites have three interesting capabilities. Because they're operating in low orbits, they can offer very high resolution. Today, we can get imagery where each pixel maps to less than 5 meters. In some cases, it's less than a meter. There have been many proposals which will bring this down to sub-meter and even more finer grained resolution. The previous slide, I talked about satellites. If you have just one satellite, you'll get probably an image of your house or a field every 5 to 10 days. Depending on the orbit. Now there are companies that are planning and already have constellations of hundreds of satellites. So this brings down the time between images to a few minutes. And finally, the hardware continues to improve. It's not just multispectral. The new satellites that are going up have hyperspectral capabilities. So you're talking of, going back to Brandon's point, a huge amount of data it's not just in RGB spectrum, and this is huge amounts of data that you really can send to the ground. A typical end-to-end pipeline right now, a cloud pipeline for Earth observation, has the following different stages. You get these either using satellite IoT, you'll get data from the ground, you have remote sensing satellites, then you have these orbital ground stations, like the one you're seeing on the left here is the one that Microsoft has in Quincy, Washington. This is one of the Azure orbital ground stations, and the one in Sweden is in the middle. And we also have third-party ground stations that we've integrated into our platform. Once the satellite sends data down to the orbital ground station, we then send all of this data to Azure data centers, where you then run artificial intelligence pipelines on top of this to do orbital analytics on top of this data. The challenge is that the end-to-end time from the time an image is taken to the time you can start getting insights is a few hours to several days. Our goal is, can you make this entire end-to-end pipeline real time? Can you be sitting in one place and seeing what's happening half the way across the globe in a few seconds? Like, for example, sitting in Seattle, can I know what's happening in Japan right now? And towards that, in our group, we've been working across the entire pipeline on different projects, all the way from IoT systems. If you deploy a sensor anywhere on the planet, how do you start supporting these sensors at scale to communicate with satellites? So we have a paper in NSDI just talking about new spectrum sharing techniques, where you can then start scaling the number of satellites, number of sensors that you can connect to satellites. We also have work on edge computing space. This is work with Brandon. The first work was work very closely with Deepak. The second work we worked with Brandon, where we have a paper in ASPLOS. So you're looking at, do you really need to send all of this data to the ground? Can you be doing a lot more compute in space itself? We also have proposed a new ground station architecture. Rather than the current ground stations, which are several $1 million per ground station, can you have a really low-cost ground station architecture? So we've leveraged the TinyGS kit to actually build a hybrid system, combining these TinyGS ground stations with the more expensive ground stations, which can actually scale and help with reducing the latency of end-to-end communication. And finally, we are looking at new federated learning approaches, where you can actually do training in space without sending all of the data down to the ground. And we are coming up with new multimodal AI pipelines, which we've open sourced. If you go to farmvibes.ai on GitHub, you'll find a lot of these capabilities that we've made available. We've also made available a simulator called Cosmic Beats. It's on GitHub, which is we started with IoT satellites, but we're making it work also with for broadband communication, which you can download and start using We've also launched a few satellites in space with a partner, FossaSat. We have about 6 satellites. And that capability, again, we would like to make available to the research community so that you can then start running your workloads or running experiments with these really low-cost IoT satellites in space. This entire space is very exciting, and we are looking to collaborate with many of you. If you're interested or you have students who want to work with us, please do reach out. Thank you.
Thanks a lot, Ranveer. So we've overrun by a little bit, but we still have time for questions. Maybe I can start off with one very general question for the entire panel. This is a completely new redesign or new way to do internet, with the routers not being in a basement in an office somewhere, but above our heads. If you had to do it completely from scratch, would you redesign the internet with satellites in them, or where do you see a place for them if you had a blue sky approach? This is for every single one of the panelists wants to answer.
I could take a first shot as I went last. So Nishanth, that's a great question, and one of the questions that we are trying to answer through the efforts on NTN. With 5G now and with 6G, people are talking about this thing of non-terrestrial networks, where networks in space go and the networks on the ground are seen as one complete network. We have that opportunity. Of course, we won't be able to redesign, but add those patches to make it work. If you were to redesign, I think you would, you'd start looking up the entire stack, all the way from even IP addressing to routing to even transport layer protocols. You would think of it end to end. It would be an interesting exercise. If anyone is looking at it, would love to work together to see if you had that clean slate, what would such a network look like?
Thanks. Anyone else has an opinion that they'd like to add? If not, maybe we can move on to a couple of the questions in the Q&A. There's one question about what simulators were used. I know Debopam has in the past done something called Hypatia on an S3. I know there's something called StarryNet, which appeared in an SDI last year. But if there are simulator approaches that any of you in the panel have used or think is useful for the community, maybe you could enlighten us about that.
Yeah, definitely. That's something we've been looking a lot at. What's the right set of simulation tools to model computational applications in this area? The go-to Swiss Army knife toolkit for operators in the space world is STK, and it does a lot of things really well, including good physics-based modeling and slurping up all the data that you can get about the orbits of many satellites, and you can do local body dynamics, and you can extend it. It's really nice. It's a good system. One thing that it doesn't do well is model the dynamics of computation and the connection between the orbital dynamics, energy collection, and computational efficiency, which is something that we've been looking at very closely, and it determines the value of a constellation. If you have a limited amount of energy coming in, you have a limited amount of compute capability in the box, then you need to understand what should the actuations be along the course of the orbit track, what pointing actions are you going to take to do data acquisition or to do improve your rate of charging by pointing your solar panels into the sun or something. And so that's something where we developed a simulator. It's called COTE, C-O-T-E. And that simulator was something that was born completely of necessity. We used that to do our research on orbital edge computing and constellation modeling. And we're looking now at how to plug that into simulator data sources that come from a variety of sources. For example, Planet has a huge data source. They're a major resource in this area. So pulling in Earth imagery data and then having a reasonable computational model and a reasonable physics model. The challenge is really bringing all these things together so you don't get like a piecemeal simulator that works for part of what you're trying to model but leaves out this really important other aspect. I think I also probably should mention cesium, because cesium is like the front end for everything. And another big effort we have going on is making this all really plug and play, point and click in a cesium-based infrastructure. And I actually have got about 5 students pushing on that right now. It's a major undergrad side project that they're working on. So anyway, the simulation thing is super important. We learned a lot just by building the simulator too. So if you have a new problem that you think isn't handled by STK or by COTE or by any of the other simulation options, I strongly encourage you to get your team to go and try building a simulator. You'll learn something about the problem by having to model the problem. It's kind of the same principle as if you want to learn something, go teach it. So I hope that's helpful.
Completely agree. Yeah. Any other tips for simulators that anyone else has? If not, there's a question here about how much energy can a LEO satellite capture and store in 1 hour orbit to support communication and computing? I guess it's about the energy budget of a constellation.
Well, I have that handy in my head. If you do 3U satellites and you do surface-mounted solar panels, you get about 7.1 watts of power. And if you integrate that over the course of a 90-minute orbit, then you just have to multiply by however many seconds are in 90 minutes, and there's your amount of joules that you can collect. That's pretty fixed, and you see the problem if you're thinking about computing. That's what makes computing in this situation really hard. So,
yeah.
That's a specific answer just to that question. There's a broader topic here of what do you do with all that energy, but I'll let others talk.
A very good calculated answer. François, you want to add something?
Yeah, so it was more related to the simulator question. So I don't know if I get back to that or.
Yeah, of course, yeah.
So we've worked quite a lot of packet losses because I did my thesis on packet losses basically and how to recover it. And something that I first learned the wrong way is that losses do not really happen. Like, for instance, NetM would show them appear. It would be, for instance, if you have a Wi-Fi link or a Starlink link, you sometimes have like retransmissions and stuff. And so sometimes packet loss also are highly correlated with a jitter and some delay. And so if some researchers want to perform some experiments, it's important to make sure that these losses are well simulated and not only done in a uniform manner. Otherwise, you will think that you were able to recover losses easily. But if it's, for instance, tightly correlated to some delay, sometimes, for instance, in my case, I was sending FEC. The FEC was arriving a lot after the loss occurred just because of that jitter. And so if you have a simulator that is just simulating random losses, it just won't work. So that's something important. And I know that Starlink has some retransmission technologies also. So it's important to take that in mind as well.
Yeah, that's a good pointer. Maybe one more question is about the motivation for these kind of satellite network operators is to have larger coverage in places that are not yet covered. But in terms of the price points, they're not yet too favorable for the so-called global south. So do you really think that there is an opportunity here to connect the unconnected, or where do you think the limitations might be for these kind of constellations? This is for anyone in the panel, I guess.
I could start. Lili, you haven't answered. I'll let Lili, or anyone else who wants to go. Sorry, from Mohamed.
Go ahead, Ranveer.
Okay, I was just saying that, with any of these technologies, in order to scale, we need to start showing the feasibility and getting users. So I think satellites space communication at least is needed to get there. And regarding this question of connecting the unconnected, it's an important one, given that over 2 billion people in the world are still not connected. There was a study we recently did. This was a paper we published in Communications of the ACM with the Gates Foundation, where we looked at, we talk about 40% of the world who's not connected to the internet. But if you look at the GSMA reports from cellular operators, they say over 90% of the human population is under cellular coverage range. So the disparity here for 30% of the population is not that they are not in cellular coverage range, but that this is not affordable for most of the population. And once we talk about affordability, part of it is a technology problem, which we can solve, but part of it is also a business and a policy problem, which I think needs to be addressed as well. The first part is to show the feasibility, which is what I think existing space networks are doing. If people can come up with lower cost solutions, that's great, but I think it would have to be a joint technology plus policy plus business solution. which we as technologists would actually have to reach out to some of these policymakers, business folks, and try to figure out what the solution is. And I think we are moving in the right direction. It's moving slower than we would have wanted because the problem is severe. This is causing that digital divide in the world. But we are taking the right steps.
Yeah, it's a proof of concept, if nothing else. There's one more question, which I think will have to be the final question since we are coming up to the hour. This is asking about people talking about moving computation to space, and whether there has been thought given to what types of physical infrastructures we should expect in orbit. What does a space residing infrastructure providing SDX services analogous to a cloud or data center on Earth? What would it look like in space? If anyone wants to take a stab at that.
Sure, I can take a swing at that one. There's a few things that are unique about being in space, and one is global access to sensor data. You're flying around, you see the entire Earth. It's like a line scanner for Earth if you're doing Earth observation data, and you're able to grab all the RF signals that are available to you within a very broad area of what you can see on Earth. And that's quite unique. So at least with respect to sensory constellations that are designed for cyber-physical systems applications, which is my primary focus and interest in this area, I think that we won't see something like the cloud per se, because the cloud is in a sense passive. It waits until you send it things that you want done, and then it'll do those things for you, and it doesn't really make any judgments. But there's an opportunity for an infrastructure that does a lot more, and that is as an infrastructure, it's able to make decisions about what is important to a collection of applications, and that means, making judgments about what sensor data should be prioritized and what sensor data should be relegated. And these are features that they may have analogous components in terrestrial cloud systems, but they seem fairly unique to me, and we're only really just beginning to understand how do we build a system, how do we architect an infrastructure around that. And this is sort of virtual description. There's a physical description that goes along with this. You need sensors, you need onboard compute to make these kinds of judgments. You need actuation too, because if you want to follow through on making those judgments with autonomy, members of the constellation need to be able to change dynamically what they're doing. Usually that means pointing, but there's also another form of actuation in a sense, which is communicating between members of a constellation. So physically, they're going to have to be equipped with high bandwidth crosslinks and high bandwidth downlinks. So there's actually, I think, a very open area of engineering and research that's going to go into this. Like I said before, we're trying to build a research constellation right now to help answer some of these questions. We would be happy once we have those satellites flying, some of which are already flying actually, to take your workload and try and do something with it. But I think that this is a big open question in our area right now.
Thanks a lot, Brandon. And with that, we'll have to conclude the panel. Let's thank the panelists for their contributions. We tried to highlight every aspect that we could of this new emerging area of LEO mega constellations, so ranging from metasurfaces and signals and how do you transmit those signals right up to space, all the way to internet measurements, to different kinds of applications and compute in space and so forth. So I hope that gives you a little bit of a flavor. There's quite a lot of work going on. Please follow. There's also, for those of you who are interested in this, there's the LEOCon webinar series that Mohamed and Debopam mainly organize. If you Google search for LEOCon webinar series or leoconws.github.io, there'll be other such webinars happening one every other month. I think is the cadence there. I hand it back to you, Matt, to conclude.
Okay, yeah, we want to finish by thanking the panelists very much for their insights and putting together such an interesting event. We're going to have a recording of the session put up on YouTube. It's going to be linked off of our website. We want the conversation to continue on the Slack. Feel free to join the workspace that's been mentioned in the chat here on Zoom. If you have further questions for any of the panelists, they're happy to continue discussing with you. Please join. Feel free to message them. This is going to be our last event of the year. We're going to start up again in mid-January 2024. So thank you, everybody, very much.
Thanks, everybody.
Okay, and thanks to the organizers.
Thank you.
Yeah.
Thank you.